Hi, this is lecture 22 of Applied Statistics. While this class overall is calculus and linear algebra based, I want this particular lecture to not depend on those subjects too much, to be applicable and useful for a wider audience. There's no calculus at all in this lecture, in fact, and the linear algebra I'm keeping to a minimum until the very end of the lecture. So if you are in a class where you need some details about the mechanics of inference for multiple regression, you'll still be able to get a lot out of this. We'll focus on using a spreadsheet and looking at the output from the spreadsheet and how to find the answers that you need. I'm doing it for a home prices example based on data that I personally gathered back in 2014. Here's the lecture plan. So I'll start with how and when I gathered the home price data. I'll move on to looking at the variables of interest, including one categorical variable. I'll make comments about the validity of the conclusions, and what we will see, the comments that I'm going to make, is that the model here that we look at is actually not ideal. Then we'll look at the variable names and the introduction of something called an indicator variable, which is related to the categorical variable. Then we'll look at the multiple linear regression model in terms of a design matrix. This is the one place in the middle of the lecture that I'll talk about linear algebra, but it's a real short amount. Again, most of the linear algebra comes at the end. We'll look at the spreadsheet use and output. We'll look at how to find answers for the confidence interval estimates of the parameters, the betas. We'll look at hypothesis testing for those beta parameters. We'll also look at hypothesis testing for the overall model. Is the overall model significant or not? Along with that, we'll look at the coefficient of multiple determination, R squared. Something we can't do so easily with a spreadsheet is looking at confidence intervals for estimating mean response and prediction intervals for an observed response. So I'm going to have to rely on some formulas at that point that do relate to linear algebra, and this is where the linear algebra starts to come back into play. You can still trust those formulas, and if you don't know about the linear algebra, you can ignore it at that point. We'll talk about the relationship to matrices here. That's the linear algebra. Finally, at the very end, I'm going to go into using Mathematica, which is what I use with my students, and teach my students and anybody else who's interested how to use Mathematica in this context and get some output. As usual, the lecture documents can be found in the link in the description below. All right, so here's our practical example, trying to predict home prices based on some other data. This is page 1 of that. So it's back in June of 2014. I went to a real estate website and gathered data about homes for sale in Roseville, Minnesota. Here's Minnesota. You can see Minneapolis in that picture there. Roseville is where the red marker is. If you zoom in closer, you can see that Roseville is right here. So it's pretty much between Minneapolis and St. Paul. Minneapolis is about like this, and St. Paul is about like this over there. So my sample size was actually all the homes that were for sale at that one day in June of 2014, and there were 87 homes for sale. I can think of that as a sample from the larger population of all homes in Roseville, if I like. Is it truly a random sample? Well, not truly, because it's particular homes that were on sale, but you know, that's random enough that it's probably decently valid to call it a random sample. You could also call that the number of cases or observations, again, n equals 87. I gathered data about 4 quantitative variables: square footage of the house, number of bedrooms, number of bathrooms, and the asking price. Okay, now asking price is, you should realize, is something different than both sales price and assessed value. The sales price is what somebody actually purchases it for. Could be higher, could be lower than the asking price. The asking price is what the person selling the house is asking for. Assessed value is a different thing. It's an assessor has to come and estimate the value of the house. That could be yet a different number. I also gathered data about one categorical variable that did not have numerical values, what I called the style of the home, and I initially classified it by the following categories: an older rambler, essentially anything built before about 1960 or so; a newer rambler, style, an older style but newer than 1960; colonial, split level, townhome, condo, and then sort of a catch-all term here, modern, for things that were, you know, newer in the last 20 or 30 years and didn't quite fit the colonial, say, form, or any other form for that matter. However, for the purposes of simplifying this particular analysis, I decided to reclassify these things. The older Rambler gets classified as older, and everything else I lump together as newer. Okay, now that might be debatable whether that's a good idea or not. It seemed reasonable to me, and when you're developing models like this, reasonableness is oftentimes a criterion that people use. In reality, I should do exploratory data analysis before doing any formal regression modeling and statistical inference. Okay, that really is an essential practical thing that you should do. You always should explore your data before you think about doing regression modeling. I'm saving that for the next lecture, lecture 23. In this lecture 22, I'm focusing on the mechanics, so I'm going to go ahead and do the regression analysis anyway, but realize that in real life, that's backwards from what you personally should do. Okay, so I'm doing bad practice. It's bad practice just to do a bunch of calculations without looking at or exploring the data. Again, for purposes of this lecture, we'll go ahead and do our regression analysis and statistical inference anyway, keeping in mind that our model and conclusions may not be valid, and as well, our model may not be ideal, and in fact, we will see it's not ideal. The main goal is, again, to talk about the technical details of constructing the model, computing various interval estimates, and doing hypothesis testing based on the spreadsheet output for the most part. We'll save that other stuff that's more important at the beginning for the next lecture. It's going to be the same data, but we'll talk about the exploratory data analysis. To help understand what's going on more clearly, we're going to use variable names that help describe what the variables are. Otherwise, it's too easy to forget what the variables mean unless you give them descriptive names. So I'm going to use SF for square footage, bed for the number of bedrooms, bath for the number of bathrooms, and P for the price. And that really, again, is the asking price. How about the categorical variable? Well, it was either older or newer. Well, I'm going to use the symbol new as what's called an indicator variable. Now, I haven't talked with my students yet about indicator variables, and maybe you haven't heard of them either. I'm telling you right now what they are. This new variable takes on only one of two values, and they're numerical values, not categorical, though they're kind of fuzzy numerical values, so in a sense they're categorical, but we will still use them in the formula. I'm going to say new equals 1 if a house is newer, and new equals 0 if a house is older. Okay, older Rambler is going to have a value of 0. Everything else is going to have a value of 1. There are actually a lot of older Ramblers in Roseville, Minnesota, homes built before 1960 that sort of fit the Rambler type. All right, so again, this makes the categorical variable into what you might say is a somewhat fuzzy quantitative variable. You know, what is newer really? I'm oversimplifying things is maybe one way to think of this. Our goal is to predict P. So SF, bed, and bath, and new are going to be explanatory variables, and P is going to be a response variable. Trying to predict P, the asking price, when we know the values of the other variables, as well as do inference about the wider population if other homes in Roseville, Minnesota went on sale back in June of 2014. What would we predict about those other homes? Keeping in mind, again, that our model may not be very good. All right, so what's the form of the model? What's the abstract form? This gets a little abstract here, but it is really important in constructing the model. We start with the mean. The mean asking price, mu sub p, represents the mean of the asking price for a particular square footage, a number of bedrooms, a particular number of bathrooms, and whether it's new or not. 0 if it's old, 1 if it's newer. And you've got these constants, beta 0, beta 1, beta 2, beta 3. This is standard notation for the coefficients of these things. Beta 0 is the constant term. You know, with one variable regression, it's the y-intercept. Is it an intercept in this context? Well, yeah, if you allow yourself to imagine a higher dimensional intercept. You know, there's 4 independent variables and 1 dependent variable here. You'd sort of be thinking about 5-dimensional space. Oh, well, I better not go there anymore. Okay, it's just the constant. Let's just think of it that way. You can think of the other betas as being rates of change. Should I call them slopes? Well, it's probably better to call them rates of change, because they are the coefficients of these linear terms. SF, bed, bath, and new are all to the first power. Do they have to be the first power? No. In fact, if we were doing a little exploratory data analysis, we might see it would be better to take one of these to the second power. It's possible, okay? But we're keeping things simple here. All right, that's the mean. It's a linear function of those variables. And then individual responses, call those PI, are the mean of all the P's for the particular SF, bed, bath, and new, plus some error term that's random. It could be positive, it could be negative. EI is the symbol for that random variable. Some books call it epsilon I. The EIs are all independent and identically distributed random variables with common distribution that's normal with a mean of 0 and some positive variance. The notation here, sigma squared, means variance. Some books just put the standard deviation there, which is just the sigma, which would be the square root of the variance. But my book that I use uses the variance there. What's the design matrix? So here's a little bit of linear algebra. This is the main linear algebra in the middle of this lecture. Save the rest for the end. It's an 87 by 5 matrix, 87 rows and 5 columns, and the y vector for the price value, which I could call it a p-vector here, is 87 dimensional. There's the matrix, 87 rows and 5 columns. There's the y vector, which are really asking prices. I could have called this a p-vector, but I'm being consistent with the notation in previous lectures here. You put a bunch of ones in the first column, you put the square footages in the second column, you put the number of bedrooms in the third column, the number of bathrooms in the fourth, and the new indicator variable values, 0 or 1s, in the last column. By the way, the number of bedrooms we're taking to be a whole number. It's either going to be 1, 2, or 3, or 4 typically. The number of bathrooms is often a whole number, 1, 2, 3, or 4, say, but sometimes it takes on a value like 2.5 or something, because there are some bathrooms that are classified as half bathrooms. For example, if they just have a toilet and a sink, I think officially that's a half bathroom. Okay? All right, that's just a little bit of linear algebra for the moment. Again, more later. At this point now, we're going to look at spreadsheets. So here are the results of the spreadsheet regression analysis. This is the summary output that you would get. You may want to take a picture of this, maybe pause the video, get your camera out or something, take a picture of this. I will come back to it in another slide here. But I'm now going to go to the spreadsheet and show you how to get this output if you don't know how already. Then we'll go back and analyze this, look for the things that we're interested in knowing. So I'm going to go to a spreadsheet now. Here it is. So this is a Google Docs spreadsheet. You can do what I'm going to show you in Excel as well, though it seems to work better on PCs than a Mac, and I have a Mac. So I'm going to do this in Google Docs. There's an add-on that you should get if you don't have it that can help you do what I'm about to show you. It's called XL Minor Analysis Tool Pack. And if you don't happen to have that, then you should go to Get Add-ons and search for it. XL Minor, M-I-N-E-R, Analysis Tool Pack with a P-A-K for the pack spelling there. That's the add-on that we want to use here. And we're going to do linear regression. Okay? So we're about to try to get that output that I was just showing you in the PowerPoint slide. I always make a habit, first of all, of including the labels. So I click this labels box here in the lower right corner. And when you click that box, you better include the labels. The labels are the variable names here, SF, bed, bath, new, and P. By the way, I'm emphasizing here P is in thousands of dollars, so that's good to remember. There's 87 data points. The first data point is in row 4, so that's going to make the last data point in row 90. I go down here. You can see it's row 90 right there. Ignore this stuff. There's some summary statistics there. So I can highlight that entire column if I like, but I think just so it's not goofy with some things it might do, I'm going to just go ahead and type it here. So I want to go F3 through F90. Notice I type F3 colon F90. That's the input Y range. Then for the input X range, I want all the explanatory variables. So it's cell B3 in the upper left corner to cell E90 in the lower right corner. So I can type B3 colon E90 here. Oftentimes I do residuals and residual plots, but I think for the moment I won't bother. I'm going to put the final output that we saw in the PowerPoint here, where the output range is the upper left corner of the output. It's going to be in cell H4. Okay, then click OK. And once this is done, then we get the summary output that was in the PowerPoint. Okay. So I'm now going to go back to the PowerPoint and we'll glance at that, and then we'll focus on what are the answers. This is the mechanics of using the spreadsheet output to answer questions. We'll start with the bottom here. It's usually where people start, right here. We see intercept, we see SF, we see bed, we see bath, we see new. We see the word coefficients. These numbers are the sample estimates for the unknown parameters, the beta 0, beta 1, beta 2, beta 3, and beta 4. Typically, people call these B0, B1, B2, B3, and B4 for the sample estimates of those population parameters. The population parameters are fixed numbers, but unknown in the model, if the model's good at least. These sample statistics in the abstract are random variables that have distributions. Different samples would give me different values. This particular sample of size 87 that I picked on this particular day of June of 2014 give me these particular sample statistics. B0 is about negative 11.6, B1 is about 0.17, B2 is about negative 46.567, B3 is about 47.88, and B4 is about negative 16.83. Okay? Before I go on, I wanted to mention this earlier, but I forgot. Realize that there's something that might seem a little fishy about these. And this is sort of an indication of this model not being ideal. You would think, and I would think, starting with the model, that as the square footage goes up, the price should go up. As the number of bedrooms goes up, the price should go up. As the number of bathrooms goes up, the price should go up. And if it's newer, the price probably should go up. Meaning all these coefficients, except perhaps the intercept, should be positive. But they're not all positive. The coefficient of the bedroom is negative, and the coefficient for newer is negative. What's going on here? Seems like kind of a mystery. Shouldn't those all be positive? Well, it's partially because this model's not ideal, and it's trying to do its best to estimate the data as a whole based on all these variables. But the fact is that these variables are correlated with each other. If you've got more square footage, you probably have more bedrooms and you probably have more bathrooms. If you've got more bedrooms, you probably have more square footage and you probably have more bathrooms. These things are positively correlated with each other. It's sometimes called collinearity. And I think that's what's messing with these things and making some of these coefficients negative. It might still do a decent job of making some predictions, but it's still not quite ideal. Maybe we should be getting rid of some of these variables. That's sort of the big picture here. So we get all positive coefficients, because these coefficients as they are, including some negative one, would lead us to some conclusions that don't really make much sense. Like as the number of bedrooms goes up by one, say, the price should go down by $46,560. That seems silly, okay? So it's in that sense, and in trying to interpret these rates of change, that the model is, you might say, deficient. And we probably should get rid of one or two or maybe even three of these variables, okay? Maybe multiple regression, in fact, is not the best approach to use. What else do we want to look at here? Lower 95% and upper 95%. These are lower and upper bounds for confidence intervals, 95% confidence intervals for the population parameters, beta 0, beta 1 through beta 4. We also see t-stats and p-values. Those are going to be t-statistics and the corresponding p-values for certain hypothesis tests on those parameters. We see standard errors. Now, I haven't really told my students what standard errors mean. I'm going to tell you and my students in this lecture what those mean. We will also look at the ANOVA output eventually here. And a little bit we'll look at up here. We'll mostly focus on R squared, which is about 0.827, and the standard error, about 85.3, and what those things mean. Okay? So again, if you haven't taken a picture of this, you might want to take a picture of it before we move on. All right, and moving on, let's look at the details of the answers more clearly And now I'm also going to show some formulas. Let's look at the results step by step. First, here are the 95% confidence interval estimates for the population parameters. We have the point estimates. Those were the coefficients, B0, B1 through B4. But those are point estimates. Usually you want confidence intervals with statistics when you're doing inference, because you shouldn't expect the sample statistics to equal the population parameters exactly. You want some cushion. For the intercept, the answer from the spreadsheet for the lower and upper bounds are these numbers. Okay, so that's what comes from the spreadsheet output. I also have formulas here. Got this formula and this formula. And I also wrote the answer in plus or minus notation with the point estimate here and the margin of error over here. Focus on the formulas. My students should focus on this form of the formula initially. This is what you'll find in our textbook. My students use this textbook right here by Milton and Arnold. And based on the previous lecture, my students should know, for example, what C00 means if it's related to a matrix. I haven't shown my students this notation before. SE here stands for standard error of B0. This number is essentially an estimate of the standard deviation of what's called the sampling distribution of B0. If you think of B0 as an abstract statistic that can take on different values for different samples, it's going to have a probability distribution, a probability density. And this SE is an estimate for the standard deviation of that based on the sample. S is the regression standard error. These two things multiply together to give you this. We have the t value here, t sub 0.025. Based on how many degrees of freedom, n is 87 here. We've got 4 explanatory variables. That actually means df, the degrees of freedom, is n minus k minus 1, which is n minus 4 minus 1. N minus 5 is 87 minus 5 is 82. We have 82 degrees of freedom. Keep that in mind with all this, and that we tell you what the t is. I think I have it written somewhere, but I don't remember what it is offhand here. Okay, this SEB0 though, I'm going to go back to the spreadsheet here. That's the standard error column here. SEB0 is this 35.0464683. Okay, that's what that number is right here. Okay, and you can just double check these things. So this is for the intercept. It's a pretty big interval. It contains both positives and negatives. Boy, that's so big it seems like it's maybe not even useful. And its units would be the same as the units for P, which would be in thousands of dollars. Wow. Even with a sample size of size 87, this is still a pretty big interval. How about the other parameters? Beta 1, for example, which is the rate of change of the asking price with respect to the square footage. It is a positive thing here. It's a small point estimate, but remember what the units are. This would be then in thousands of dollars per square foot. So for each extra 1 square foot, this model seems to be saying your extra price would go up by $0.17,000, which would really be about $170. So even though this is a decimal, it's representing bigger dollar numbers than you might think initially. It's probably better to think of in terms of not increasing the square footage by just 1 square foot, but maybe more like 100 square feet or something like that. Anyway, this is the answer in the spreadsheet. You can check in plus or minus notation that it's about this. By the way, these numbers don't necessarily match up precisely because of rounding. B1 is the estimate for beta 1. The confidence interval formulas over here have a very similar form, as they always pretty much seem to do with these. In this case, we're using a t-distribution that's symmetric about 0 in these plus or minus confidence interval formula notations. Once again, SEB1 is a standard error. You can find it in the spreadsheet under that standard error column for estimating beta 1. S, by the way, I haven't told you what S is yet, its value. It's the regression standard error. It was in the spreadsheet output. I guess we did briefly look at it. I think it might have been 85 or something like that. At the very bottom of this particular slide, we will see its value as well. And again, the C11 corresponds to something in this textbook that corresponds to a certain matrix. It's some linear algebra stuff that I'll talk about more later. Beta 2, the coefficient of bed, the rate of change of the asking price with respect to the number of bedrooms. The spreadsheet output and the other stuff is very similar. Beta 3 is for the number of bathrooms, including if you add in a half bath. And this is the answer. Notice this one contains all positives, this one contains all negatives, this one contains all positives. And again, it may not make sense that, for example, for the bedrooms, that you would have a negative slope, negative rate of change. That really is hard to interpret. Once again, that means this model is maybe not ideal. This collinearity between these variables is probably what's messing that up, so to speak. That's what we'll focus on in lecture 23, is finding a better model. Beta 4 is the coefficient of nu. And again, here is the output in the spreadsheet and the other formulas. And yeah, I have here S is about 85.3. Formula for S is square root of SSE divided by n minus k minus 1. SSE turns out to be, I haven't verified this, this number, 596,651.1679 divided by the degrees of freedom, which is 82. Take the square root to get S, the regression standard error. Actually, this 596,651 SSE is in the output. It's right here. Okay, it's SS for residual. SSE means sum of squares error. Error is synonymous with residual. We'll talk more about that here in a bit. How about hypothesis testing? Excuse me while I get a drink of water here. We can do 5 hypothesis tests on the population parameters beta 0, beta 1, beta 2, beta 3, and beta 4. And in each case, the p-values, the t-statistic and the p-values are coming for this test that you see here. The null hypothesis is that beta I is 0, or I can be 0 through 4. And the corresponding alternative hypothesis that our book writes as H1 and some books write as HA is two-tailed, that beta I is non-zero. So those p-values you should keep in mind. You always remember those are two-tailed p-values for two-sided tests of significance here. And that's always the standard thing to do here. And it's sort of always a good habit to do two-tailed tests, even if you have a theory that it should be positive or negative, because it sort of is a conservative approach where your p-value ends up being bigger than it would be otherwise, and it makes you less likely to make a type 1 error. The test statistics are t-statistics with 82 degrees of freedom. The BI values minus the null value, which is 0, that matches this 0 here, divided by the standard error for each of the BIs. And those standard errors can be written as this product if you like. And it turns out that these are the t-statistics and p-values you get. And the p-value for the intercept is very large, so definitely do not reject the null. The p-value for the rate of change of the asking price with respect to square footage, beta 1, very, very tiny, microscopic, so definitely reject the null. We definitely have strong evidence that beta 1 is non-zero. Beta 2 has also a pretty small p-value, reject the null there. Beta 3 has a pretty small p-value, reject the null there. And beta 4 does not have a very small p-value, so we fail to reject the null here. Keep in mind, and I mentioned this earlier, that all these kinds of things you're doing are sort of for the overall model. Okay, we're making these confidence interval estimates and these hypothesis tests based on the overall model. You know, we're making this conclusion, for example, that beta 1 is not 0, with the assumption that the other variable is part of the model. Okay, and we're seeing that beta 4 we can't conclude as non-zero with the assumption that the other variables are part of the model. Now, if the nu is the only variable that we're interested in as an explanatory variable, it's very likely we get a small p-value and we reject the null in that case if it was the only variable of interest. So these need to be thought about holistically in terms of the entire model. That's a real important thing to realize here, and I'll talk more about that in lecture 23. Getting close to being done here. Page 9, there's 12 pages on the PowerPoint. Then we'll finish the PowerPoint and go to the Mathematica. Here again is the ANOVA output, the spreadsheet output. We're now going to look at the ANOVA part of it. Focus on that right here. Real quick summary of what we're about to do is emphasize the meaning of the SS's. This is SSE, like I already mentioned right there. This is called SSR, SS regression, sum of squares. This is SST, sum of squares total. MS stands for mean square. Each of these numbers is the corresponding SS divided by the corresponding DF on those lines. This is called an F statistic here, and it's this MS divided by this MS. It's a very large F statistic with a very small p-value. This is testing the overall significance of the regression. I'll talk about what that means in a minute here. N is 87 again. DF for this model is 87 minus 5, which is 82. 4 degrees of freedom corresponds to 4 explanatory variables. The DF total is 86. Don't worry about what that means. These numbers in these two rows add up to the number in this row in each case. And I'll remind you also R squared, I'll mention what that is here again, 0.827, and the regression standard error is about 85.3. All right, how are we doing as far as a test of the overall model? Is it significant? What you're really doing there is testing the null hypothesis that all the beta 1 through beta 4 are 0 versus at least one of them is non-zero. Notice beta 0 is not included in here. That's not a typo, that's on purpose. Beta 0 is just a constant term in the regression model. What we're more interested in as far as a test goes here for an overall significant regression, to make the regression itself worth doing, is having those variables in there, so the coefficients of the variables are the important things to test here. So the null hypothesis is that beta 1 through beta 4 is 0, and the alternative is some beta I is non-zero, at least one of them. If we reject the null here, then we'll be able to say at least one of the beta i's is non-zero, though this test doesn't tell us which one is, in a sense, most likely to be non-zero. What is our test statistic? It's an F statistic. Maybe you've heard of F statistics before, maybe you haven't. F statistics come with 2 degrees of freedom, a numerator degree of freedom, and a denominator, because they are defined as fractions. The numerator degree of freedom is 4 in this case, it comes first. The denominator degree of freedom is 82 in this case, it comes second. MSR is mean square regression, MSE is mean square error, which is synonymous with residual. MSR is SSR divided by K, I already mentioned that when looking at the ANOVA output, dividing across that row. MSE is SSE divided by the corresponding degrees of freedom. I probably should have had parentheses around this whole thing here. Dividing by 82 overall there. So these are the MSR and MSE numbers, and their ratio is the F statistic value, about 98.3. The p-value is really close to 0. In my calculator, I found it to be about that, but so tiny you essentially can treat it as 0. So we definitely have an overall significant regression. We have super strong evidence that at least one of these beta i's is non-zero. Okay. Hopefully that makes intuitive sense. MSR, MSR is much bigger than MSE. This F statistic is very large. There's really relatively small amount of noise, a small amount of random error in the model. The overall regression equation is doing a pretty good job of describing the variation in the prices, in the asking prices in the model. So we reject the null. Yes, we definitely have a statistically significant regression, and we can say at least one of the betas is non-zero. What's the coefficient of multiple determination? That again is R squared. That can be found as SSR divided by SST. SSR being again sum of scores for regression, SST being sum of scores total. SSR was much bigger than SSE here. You know, that's, what is that? That's almost 3 million, whereas this is only about 600,000. So this fraction is pretty close to 1. 0.8274 as a percent, it's about 82.7%, and we'd say, this is a common phrase you hear people say, this means that about 82.7% of the variation in the asking price is explained by the regression model. The other 17.3% is from random variation, contributing to the SSE. Okay, and again, R squared was in the output. We saw it there. But you can also compute it as SSR divided by SST. Almost done here. 95% confidence interval to estimate the mean asking price for all homes with certain fixed values of the explanatory variables. I picked 2,000 square feet, 3 bedrooms and 2.5 bathrooms, and newer, so the value of new would be 1 in that case. And I plugged them into a formula for this interval. Now this formula, here we start to get into some linear algebra. Okay, now if you do simple linear regression, this formula doesn't involve linear algebra. With multiple regression, you really pretty much have to have some linear algebra ideas to write this formula nicely. Here's what it looks like. Mu hat, I get from plugging these numbers into the regression equation, the sample regression equation. Plus or minus, here's your margin of error, and this thing is a linear algebra kind of thing inside here. Okay. If you don't know linear algebra, maybe you can still stay with me to try to see the big picture. It can still be helpful, perhaps. Keep in mind, so we're trying to estimate the mean asking price for all homes with these values for the variables. Keep in mind that there could be no homes with exactly these numbers in Roseville, Minnesota. So in reality, the population is not humongous here. As far as applying this interval, you probably would apply it to homes with at least maybe this many bedrooms and this many bathrooms and are newer, where the square footage is close to 2,000. Maybe this is somewhat valid for homes between 1975 and 2025 square feet or something. And the interval is this, in thousands of dollars. And so again, this is our estimate for all of Roseville. We're doing inference here from the sample to the population of what we would estimate for the asking price that a person would ask based on these values. And we're saying it's between $267.3 thousand and $327.2 thousand with 95% confidence. Again, this is a linear algebra thing. X is that design matrix from earlier. This is its transpose. What is x0? Well, x0 is essentially a vector that takes these numbers and does this matrix multiplication in here. And this is an inverse matrix as well, by the way. There is a little added complication with the x0 vector that you have to put a 1 at the beginning. And that's sort of related to the fact that there's a beta 0 in the formula. If you don't know what this means, it's okay. Just look at the answer and think about what it means. A 95 prediction interval is to estimate an observed asking price for the next home on the market that's got these variable values, 2,000 square feet, at least approximately, 3 bedrooms, 2.5 bathrooms, and is newer. The prediction interval is bigger because we're not estimating a mean, we're estimating an individual response. And the formula is pretty much the same except you add an extra +1 in here. And by the way, this is not a typo. This actually, in spite of the fact that it involves vectors and matrices, is a number. And I guess that should have been emphasized here as well since I'm taking the square root of it. And so the y hat is also computed with the regression equation, the sample regression equation, just like mu hat. The answer is this. It's a bigger interval as you would expect with an individual home. And of course, in real life, you know, a particular home being in this interval would depend on other factors like its location and maybe how nice the home is, updates and that kind of thing. So it's a pretty wide interval. You might say maybe too wide to be useful, but it is what the answer is in this case. Okay, so that's the big picture idea as well as some of the details of these things. And x0 is, as its transpose as a row vector. 2003, 2.51 are the numbers there. This one is just always put there. You need to put an initial one. Again, it corresponds to the fact that the beta 0 is in the formula. Last page of the PowerPoint here. Where were those CI found again? From previous lectures, like lecture 21. CII, now we're getting into more details about linear algebra. That is maybe too overwhelming for people who don't know it here. So thanks for joining us if you did. Is the entry on the main diagonal of row I+1 of this square matrix, X transpose X quantity inverse. Turns out that X transpose times X inverse is this matrix, this 5 by 5 matrix. Remember, X had 87 rows and 5 columns. X transpose would have 5 rows and 87 columns. X transpose times X would be 5 by 5, and therefore its inverse would also be 5 by 5. And notice I alluded to this in, it was lecture 21, I think. You should expect that for relatively large sample sizes, all the entries of X transpose X inverse should be relatively small numbers, and you can see they are, close to 0. And that's partially what makes, I guess this came up in lecture 20, I think as well. That's what makes the consistent estimator. I guess that was lecture 21. So the CIIs are these numbers on the main diagonal. This is C00 here, this is C11, this is C22, this is C33, and this is C44. I wrote those down there. Not guaranteeing there's no typos in here, by the way, especially with the number of zeros there could be 1 or 2 extra zeros, or maybe I deleted 1 or 2. And if we use the fact that S is about 85.3, we can also compute these products that we've seen before. And these numbers are those standard errors that we saw in the spreadsheet output. Okay, so you can take the time, maybe pause the video right now and double check these things right here. All right, to finish off the video, the lecture, we're going to go to Mathematica, for my students especially, but if you're interested in seeing how to use Mathematica in this context, you can stay with us as well. I'm going to show you something extra special at the beginning here. I'm going to import data from a spreadsheet using a file path name. Now realize this file path name only works on my computer because it's where I have the spreadsheet as an Excel file, .xlsx file stored on my computer. If you were trying to do something like this and import on your computer, you'd have to use a different path name. So this is how you can import data into Mathematica. Notice the data does include the labels here. And that as a matrix in Mathematica is a kind of weird thing. It's a long matrix like this that's got like 87 columns here. And each column itself, Mathematica is treating as a vector, which is actually not quite ideal. I'm going to use something called flatten to get rid of those things. Flatten all data with labels raw. We'll get rid of those extra parentheses in that matrix, which is a better form to have it in. It actually puts it in a different form overall. That's almost the design matrix there, actually. If I get rid of this last column and instead put a column of ones, it would be the design matrix. Also get rid of the labels. I can do this drop command to get rid of the labels. So now I've got data that does not have the labels, and I can also look at that in matrix form here. By the way, the percent sign, if you don't know, refers to the preceding output. So once again, that's almost the design matrix. I can confirm there are 87 data points with length. I can look at the design, all data in matrix form. Okay, this code here will generate the design matrix. It's putting a 1 in the first column here, but because of that one there. And it's also going to get rid of the price data because I'm only going through the 4th column here. So now you see the ones all in the first column and no price data here in the last column anymore. It's all ones and zeros. It's all the new values, the indicator variable. And I can go ahead and store that in X. X is now the design matrix. And I put semicolon here so I don't have to see the output anymore. That suppresses output. Here's the asking price vector that I'm going to go ahead and call Y, though maybe I should call it P. There is the asking price vector, but I'm going to go ahead and call it Y here, stored in Y. Here's what X transpose times X looks like. It has relatively big entries, but its inverse has relatively small entries, close to 0. I'm going to call that the left-hand side matrix, LHS matrix. By the way, the matrix form just makes it look like a matrix, where if I do not put matrix form, then it does not look like a matrix, though I can think of it as a matrix. Here is what it looks like. Well, X transpose times Y, at least, what it looks like. And I can call that a right-hand side vector and store it like this. Its inverse, some people do call that the C matrix because the entries we've labeled with the letter C. Here's what it looks like. And this is the thing that was in the, what was the second to last page of the PowerPoint, or was the last page? I forgot. I can go ahead and call that C matrix. And if I don't do matrix form, it's stored in Mathematica in this form, which is, again, the more ideal way to do it as far as doing computations. Here's the observed least squares estimators. These are the B's, sometimes called beta hat. I multiply the C matrix times the right-hand side vector. This is what I talked about in a lot of previous lectures. Do X transpose X inverse times X transpose times Y. I'm solving the normal equations here, essentially. And so these are the B's. This is B0, and I get 11.6. This is B1, B2, B3, B4. We've seen these numbers in the spreadsheet output. And so I can store those, and I can define a P hat formula, or maybe I would have called it I should have called it a Y hat. Okay, it's a price estimate. Here I'm plugging in the numbers 2003, 2.5, and 1 for the confidence interval and prediction interval near the end of the PowerPoint. 297.256 is the point estimate. It's mu hat and also y hat. I can do other things. I can, what did I do here? Oh, I think I did this so that I can focus on the residuals. Here are the residuals. I'm not really going to go into detail about this. Actually, these are the predicted values, p hat values, as a list. These are the residuals. Here's the squared residuals. Here's the SSE, sum of squares of errors, which are sum of squares of residuals. And here is the regression standard error, about 85.3. And we can do confidence intervals to estimate the population parameters. Here's the t-value for 95% confidence based on 82 degrees of freedom with more significant digits than you typically would have. But I'm doing this so that when I enter these things, it matches what I had in the spreadsheet better, or the PowerPoint better. And I guess that would also match in the spreadsheet better as well. So these are each of those intervals that were in the spreadsheet. And then I can do the confidence intervals to estimate the mean and the prediction intervals here. This ends up being kind of funny. I couldn't quite get it to work real nicely. I had to drop the leading one before I could plug it into the p hat function. Don't worry about the details of why this code works in the way it does. This does give us the final interval for, this is the confidence interval to estimate the mean. And do similar stuff, and I can do a prediction interval to estimate individual outcomes. So these intervals here, this one here, and this one here were on the last slide or two of the PowerPoint. Okay, lots of detail there, I know, but real important if you want to know the mechanics of understanding the spreadsheet output, and for my students, even understanding more with the matrices and Mathematica usage. So I hope it was worthwhile. Thanks for watching.